So in this presentation, we're going to have a look at IDS, or intrusion detection systems, and see how important they are in detecting a range of threats. Okay, so we'll look at some basic attack patterns, and then we'll look at an example of an IDS, and that is with snort, and then some basic types that we can set up our IDS system. Okay, so let's look at what an attack pattern actually looks like. Well, this is one that we would see, and what we really want is for our IDS system to be able to detect an intrusion at an early stage. So it might be from an insider exploiting the system, or it might be from an outsider to a company, but very much we want to be able to detect the early signs of a threat and to be able to stop it from going to profit. So in the first stage we might define as outside reconnaissance, and that's where an intruder might use DNS information or WHOIS databases or job sites information and so on, and generally try to understand the infrastructure of the company and the people involved. Then there might be some inside reconnaissance that would go on, such as discovering open ports, hosts that are enabled, and so on. After that, an intruder may look for an exploit, try to find weak passwords, weaknesses in firewalls, and so on. After that, we may see the intruder then getting to the point where they gain a foothold on the system. So it might be a low-level account and then an escalation up onto there. And then finally, the intruder will get to some sort of profit. So there tends to be several states that are involved, and it can take some time to go through each of the states. So we often have to set up an intrusion detection system at each point to be able to possibly detect an intrusion. If we can detect it, then possibly we can stop it from getting to this profit point. Another model which is used is what's called the Lockheed Martin kill chain model. That looks at reconnaissance, weaponization. So that's where an intruder might define a weapon, a piece of malware that could attack the organization. That's then delivered through some sort of exploitation. There's an installation, a callback to command and control, and then some sort of actions on an objective. Okay, so we can place the IDS at many points inside the network infrastructure. Remember, this could be cloud-based, so this architecture could be in the cloud, and we could have virtualized firewalls and so on. So if this is the main gateway for the organization, then we might set an IDS here, and that will detect the intrusions that are detected here but don't get across the firewall. So there might be a spear phishing attack or denial of service that will happen on the other side of our firewall that we can't see in the organization, but we're sitting on the other side, we can actually see it. And here we'll see the ones that get through, so we could try to detect an intrusion at this point. But the problem that we have here is that the rate, the traffic that flows at this point can actually be extremely high. So it's actually very difficult to set up an IDS here. Then we might have a firewall. So this is our untrusted network. This is a DMZ, and this is a private network. And again, we might have firewalls along the way. Eventually we get to a switch that will connect our hosts. So we could add an IDS system onto our local networks, and we could also apply it onto our hosts, so to be able to detect an intrusion on the host. A problem that we have with IDS systems is that if we go through the network, then a lot of the traffic might be encrypted until it gets to the host. And it's only at the host that we might be able to detect an intrusion once it becomes unencrypted. Another place that we might place it is in the DMZ, and we might add an IDS onto our web servers and so on. Okay, so we can place it onto our servers in our DMZ. Might place it over here, place it in an internal network, and so on. And really, we can have many IDS systems across the network, and we should be able to detect possible intrusions at different parts. If an intruder is in the network, then it can be difficult to be able to detect it through a firewall, especially if they're using tunneling techniques. So let's look at an example of an IDS, and this is an open source package called snort. So with snort, what we do is we define a set of rules, and then we look at it generates event data. So the event data might have true intrusions, or it might have false intrusions, true positives or false positives. And we also get some log data in there too. The two main types that we have are signature detection, and these are quite good for detecting standard signs of an intrusion, such as a well-known malware or a certain attack tool. What's not so easy to detect is with anomalies, and with this we have anomaly detection. So with anomaly detection, we're looking for something that doesn't quite look normal, such as an increase in the amount of logins from a certain user, or when a user is changing files that they're not meant to change. The rule itself, the rules are fairly simple, and we see an alert. Then we define the protocol. So the protocol can be TCP or UDP here. We then define the source address and the destination port, the source port. So this is the port number, and this is the IP address. Then we identify the destination IP address and the destination port. So we can see we can use a slash format. So /24 identifies the first three fields here. /16 identifies the first two fields. /8 identifies the first field. And that will match the network part of the address. After this, we can actually define, in this case, the content that we're looking for. This is a hexadecimal pattern, and then the message that we have. One thing that we must do is add in an SID or a snort rule identifier. Okay, so we can detect binary content with hexadecimal, or we can have a text sequence if we require. So here are some rules here. So we can also have global variables that will actually define, say, a range of addresses that we want. So in this case, this is alerting for TCP from the SMTP servers on any port to port 25, which is the SMTP service. In this case, there's the message that's displayed. We can look at the flow and the content of the message. And for this, we use deep packet inspection, where it will mine any part of the TCP payload. Okay, so then again, there's the content and so on. Okay, we'll see here that each one has got an SID associated with it, and each rule must have its own SID. In this case, at the bottom here is a connection to port 21, which is the FTP server, and it's looking for whenever there is a command CWT and also ~root, and that's where the person who's logging into FTP is trying to change the working directory to the root account. Along with this, we can have what are called preprocessor rules. And in this case, this is a rule that allows us to be able to detect for a scan on the network. So in this case, it will scan whenever someone does an Nmap scan. It will be able to detect TCP, UDP, ICMP, or IP scans in there. Okay, so we can add these rules in, and then it will be able to detect a standard sign of scanning in this case. So let's look at a simple rule that would be implemented. So here's one here, and all it's really doing is detecting the word "the" within inside the payload. Okay, so we normally run it something like this. We define a -l for the log folder, and it will create a file called alert.ids. So we can then view all the alert.idses, or we could send them to a syslog server, and we could read in with a package such as Splunk. So in this case, when it runs, it's reading in with the -c option, the rules file. And then we need to define the network adapter that we're going to read from. And then once it goes, then it'll keep filtering the packets. So in this case, this is what it's found. And we can see here each time it detects the word "the", we get a new alert in this file. Okay, so the information that's contained, we'll see in here the MAC addresses of the Ethernet frame, and there's the type there that identifies IP in Ethernet. Then the next part gives us the IP addresses involved and the TCP ports and other things such as the TCP element that comes next. After that, we identify the flags. In this case, it's an ACK and a push, and there's the sequence numbers and so on. So with this information, we could determine a good deal about the connection. So let's look at a few intrusions here. So in this case, it's a connection to port 1863 here. And we're looking for the content with USR and also with TWN in there, and with a distance between them of those commands. We can also add the no case modifier, which will mean that we'll ignore cases. For this, in this case, we define a class type, which will allow us to be able to identify the seriousness of the alert. Okay, so there we are. This is the source and destination, IP address and a TCP port. This is the message that's going to be shown. We can have the flow, whether it's to a server or to a client. Then we can actually define the content that we're looking for, and the depth defines in the number of bytes to look for within inside the payload, and the distance will show how far away this piece of content is away from the other one. So it's looking for USR space and then distance, and we can see this is an example here of what it's actually looking for. Each one has a rule, and we can also have a revision number on it. So we have various class types, and they really go from a high alert to fairly low. But you should never dismiss the lows, because the lows could be some sign of early activity. So we move from yellow to amber to red here, and in terms of seriousness. These ones here, attempted admin, policy violation, Trojan activity and so on, are seen as high alerts, and things like ICMP activity might be just a ping to see if a machine is online or not. A network scan might not be that malicious. Okay, so we will define these, and this will allow us to be able to classify the alerts. Okay, so here's another one here in terms of the content that it's looking for. So we can put in ASCII sequence, but we can also put in a hex character if we require, if we put the pipe symbol there. And there's file name equals 22 is the next part, and we're looking for exe, and again 22 there. Okay, so sometimes we will get scans on the network. So in this case, we're detecting a fin scan. There's a fin scan, Christmas, and so on. This gives us a way to be able to detect when there is scanning activity on the network. So this shows an example here of looking at whenever someone logs into a Telnet server. So this is the response back from the server to say that there's been a login for root. And we see that happening here, where we see a login occurring. So often what we would do is we would actually analyze the messages that are coming back and be able to detect them with snort. Okay, so possible malicious activity is a port sweep, and that's where an intruder sweeps for a given number of ports. We also get a ping sweep, where an intruder will ping the machines on the network to find out if they're alive or not. And then we could also get a login sweep, where an intruder tries lots of different logins and passwords to be able to gain entry. Okay, so here's an example here of a login sweep. We actually see a user trying lots of different usernames and passwords to be able to brute force into an FTP server. Whenever there's a success, and we see the success here, we return code 230, where before we returned a 331. So our IDS system will probably be looking for lots of occurrences of 3331, and when that happens, then there could be a sign either the user has lost their password and can't log in, or that somebody's trying to crack the password. If we see lots of 230s occurring, then we know that that is that things are probably okay. Okay, so we'll look at some examples now, and with some real rules, and see what they look like. Okay, so I've created a little example here. So I'll show you how the rules work, but if you want to check the rules on a standalone system, then you can use this page here. So I'll show just a very simple one. So this is a very simple rule to be able to detect port 21. When a connection is made, so that's to the FTP server. I'm given an SID, and the message is just FTP. And I have a PCAP of a connection to an FTP server. And then we'll just run this here. And there's the result there. Okay, so we can see exactly the packets that have triggered the IDS from there, and if you want to have a look at the Wireshark trace, it's here. Okay, but what I'll do is we'll look at some examples here. So the rules. So I'll just show how to create the rules. So we'll do FTP.rules. Okay, Okay, we need a few extra little rules here that I've included, but we basically paste in a rule here. So that's set up for us. And then I have a pcap file here, FTP2. And we'll just open that up and have a look to see what that looks like. And there it is there. So we can see a port connection to port 21 there. We'll just open that up and we'll just follow the stream just to see what the commands are. We can see there's been a user logged in and so on. Okay, so let's now look at our command. So this is our command here. So the first thing we need to do is to be able to create a log file. So you would make a directory called log, which is the default. And I've already created it anyway. So I'll just remove it anyway and recreate it. So I'll make a directory called log. Then what we'll do is we'll run snort -c, and then we've got the rules file, and then -r, we add the pcap file. So normally when we would run this, we would actually define the network adapter and not the pcap file. So if we were to run this in real time, we wouldn't have that. We can then add in -l and add the log folder, but I won't do that just now. So this is going to check our rules to see if it actually works, and it runs through very quickly, and what we should see is a number of alerts. So you can see here 42 alerts in there, and if we go into the log folder, there's our alert file, and there are all the alerts for a connection to port 21 on there. Okay, so you can see all of these here, and they give us the details. So the great thing with the IDS is that whereas Wireshark shows us all of the detail, this is now just showing us the information that we want. So the next one we'll look at is just a little advancement on this. So in this case, we'll add this rule. Okay, so in this case, we're going to detect again the FTP connection, but now what we'll do is that we'll detect the 530 user. So the 530 user was when there was, if we look back, a bad login. Okay, so we'll just save that. And from there. So in this case there was 2 alerts. So now if we go into log, we'll have a look at alert.ids. In this case there was just two connections there. Okay, so now what we'll do is that we'll run this. So we'll just delete the previous alert file, and we'll just bring back our command. And in this case, I have a file called Hydra FTP, which includes a whole lot of bad logins. So we can see here what has happened is there are 57 alerts here. So we'll just go into the alert folder, again, into log folder. And we'll have a look. And there we go there. Okay, so we're seeing bad logins occurring there, 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 and so on. So this would be a sign of possible maliciousness where there is a continual probing of the of user accounts. So if we have a look at this Wireshark trace, what we should see is lots of attempts to log in, and we see here a response of 331 for the user being asked for their password, and then a 530 in terms of the user not being able to log in. So if we wanted, we could just search for these, response equal to 530, and here they are here. So you can see the number of times that that we get the 530 alert there. Okay, so in this way we can set up our IDS to be able to pinpoint the detection of the bad logins. So we can try with a detection of Telnet. So we'll get some rules for that one. So in this case, it's just detecting port 21 for a Telnet login, and then we can just run this command here, which has a pcap file with Telnet. And again, we see that we should create a number of alerts. In this case, we've got 72 different alerts. So what happens is that the alert file just keeps building up with our alerts. So every time that we run it, then it will just append onto the end. So we can see here we've got our FTP ones here, and these are our Telnet ones and there. Okay, so an interesting one is to be able to detect certain file types. So as we've seen, we have magic numbers within inside files, such as 89A for a GIF file, %PDF for a PDF file. So if we just fire that up, then we have a rules file here. Okay, so this is going to detect a GIF file, PDF, PNG, zip, and so on. So I have a file here that has an email with a GIF attachment. So we should be able to now process that. So we'll just go into our log and raise alert.ids again. And so we'll read in our rules file, read in our pcap that we've captured, and we see here we've got 4 messages. So we'll go into logs and we'll see alert.ids. And we can see it's detected 4 different GIF files in here. And hopefully if we open up the file, it should be possible to see the GIF file being transferred when we look at each of the connections. Okay, and so in this case we can also detect ICMP activity. So we'll create a rule. Yep. So in this case, we're detecting a type 0 for ICMP, which is echo reply, and the other ICMP types there. And we'll run it against a ping sweep. So snort minus C minus R, and then ping sweep. Okay, in this case there's 1500 alerts in this that have been detected, and this was because there are many, this is a ping sweep across a network. Okay, so those were some of the types that we saw there, and this is an example here. The file I should have used was email cc2, and what I'll do is I'll try it out here first just to show you that it works. Okay, so we'll put in our credit cards detector, and then it's the one that we're looking for is this one. And that is there. Okay, so it's got detected 2 different credit cards in there. If we have a look back at our Wireshark trace, if we look at our Wireshark trace, then hopefully we should be able to see the credit card details. And there they are here. Okay, so that's the rules that it's picking up here in terms of Visa card and also for a MasterCard there. So if we just check this with our snort minus C cc.rules minus R email cc2, and we should see 2 alerts here just as we saw here. Okay, so we can detect a whole range of things. The preprocessor rules are useful for things like detecting port scanning. So this is an example here of us using Nmap to be able to scan across a network and then setting up a preprocessor rule. And we see here that this is a snort detecting that scanning on our network, and it goes into a file called portscan.log. Okay, so snort itself can either be inline. So if it's inline, snort runs on an intermediate device such as a router or a firewall, and it has the ability to be able to stop the intrusions based on the alerts. It can also be out of line, where it can passively listen to the network on the traffic. Often what we do is that we send our logs to a syslog server, and then for these to be uploaded into a SIEM package such as Splunk. One thing that we might apply within our IDS is the creation of a honeypot, and the honeypot might be the first address on the network or something that looks like an interesting server. In this way, the intruder is tricked into going after the honeypot, and we can detect that before they get to our production servers. So an example of this is HoneyD. And HoneyD, we can actually create a script which will actually create what's called a lightweight honeypot. So it will look as if it is like a certain service that's on the network. Or we could create a high interaction honeypot, which is a virtual image or a real live server that the intruder can interact with. Okay, so that's given an introduction into intrusion detection systems.